All right. So, good morning, good afternoon, and good evening to our viewers from all around the world. Thank you so much for joining this live code today. I'm Anish from AppSec Engineer, and today I'm joined by Ganga Sumant, Cloud Engineer at AppSec Engineer. So, hi, Ganga.
Hi guys, hello Anish, thanks for having me.
So today, Ganga is going to be showing us something related to Azure cloud security. It's going to be a pretty interesting cloud lab that we're going to be going through. And I just want you to, all our viewers to remember that this particular lab is part of a much more extensive 4-day course that Ganga will be teaching us at Black Hat Asia in Singapore on between April 16th and 19th. So we'll be
Yeah.
including the link to that to get registered to that event down below. So check that out once you're done with the live code. So go ahead, Ganga.
Well, thanks Anish. So as he said, this lab is going to be a small portion of a much bigger class that we have planned for this event. I'm going to be taking you through a series of steps where we have a vulnerable application that we exploit and then showcase how that could then be used to exploit your entire cloud network that you have set up on Azure. So it's going to be pretty exciting. I am pumped to show you how this works. Let's
Nice.
get started.
Awesome.
Let me just share my screen. Yeah, awesome. So server-side template injection. I suppose this is not very new to a lot of you, but let me just get to the basics so we're all on the same page to start off. So server-side template injection works on the idea that in a regular web page, you have a lot of dynamic elements being rendered. And usually they might be something that are derived from user inputs. So for example, you might see websites that say, hello, your username. So it could be hello Ganga, and it is rendered at the very top of your web page that is based on what input the user is giving it. So these are expected to be input validated and they're expected to be of certain types of strings. For example, they are always supposed to be only text strings that contain nothing more than, for example, a name or maybe a birth date or something of that sort. But there is always a possibility that this is not being cleansed as it is supposed to be. And it is a potential input for malicious code. So let us say somebody is aware of how your template engine is working, and then they go ahead and inject a crafted string that is meant especially for your template engine. So in a case of a template engine, you could be using something like Go templates, or you could have Jinja or any other version of a template engine in the backend that is accepting user inputs and is trying to craft them in a way that would make sense for your application to run later on. However, if the user is able to craft it in such a way that the template engine thinks that this is something that is being given to it in the form of regular code, it could be there could be a certain parentheses or certain function calls that are being input into this very pipeline that then could potentially cause your template engine to parse this as as code instead of simple user inputs, and that could potentially lead to compromised web applications. It could lead to RCE, and in our case we are going to showcase how it could potentially lead to remote code execution, and how you could have a reverse shell that is completely able to access everything on the back end of your server. So with that small introduction in mind, let me show you an example application that we have already spun up, and it is going to be sitting on our Azure cloud services. And then we will talk about several other things that we can do to it to show you how much more of a devastating attack it can have in an environment such as a cloud environment where everything is connected and it's quite easy to like move laterally if somebody has the correct permissions that are available to them. So the application itself is a pretty straightforward application that we built sort of for this purpose as a showcase. And it is a bookstore application and quite generic. It is trying to showcase several pages, and it has a lot of elements that are quite nice to look at. However, let us say that in the course of trying to exploit this application, maybe in the course of maybe some sort of testing, or maybe in the course of uh, some black box testing sort of scenario where you're trying to break the application to figure out what is wrong with it, we find out that this application is vulnerable to uh, to template injection attacks. And the most easiest way that you've probably all seen so far is to simply try and hit an endpoint using uh, something that should be parsed. So in this case, I am going to say page, and I'm trying to find the name, which is 7 into 7. And generally speaking, this should not lead to anything. It should just hit a 404 error and not do anything else. But in my case, I see that the page is not just rendering this page, but also it is it is uh, it is computing this number. It is doing 7 into 7, and it's actually telling me the answer. So if I were to do something else, like let us say 7 into 8, and you see, so there is an actual parser that is like trying to do something with this information on the back end. So at this point, it is possible that I could sit here and try to like find other vulnerabilities, try to access the backend server itself. And it could, on most instances, it is going to be some sort of Linux machine that I could then try to like escalate backwards towards. Maybe I could do some path traversal attacks. Several possibilities are available to me, but those would be immensely time consuming. So a good thing, a good example or a good way to move forward here would be to use something called TPL map. Um, Perhaps a lot of you are aware of this one, but this is an automated tool that does that does exploitation if you already know that your application endpoint is vulnerable to template injection. This project is actually a cousin of SQL map, which is a lot more popular, but the idea is very similar in that you give this engine the endpoint that you want to test, and it is going to run a series of automated tests to try and break through. So let me show you what we're working with. So right now, let me just make this slightly bigger so you can see what I'm talking about. Yeah. So this is our lab environment, and I have this terminal is linked to my Azure account. So I have my Azure account also open here, and my resources that are available are loaded up here. Anyway, so my account on Azure, this is a sandboxed account that is available to anyone who's using AppSec Engineer's cloud, uh, services. But basically, I now have my Azure account linked to my CLI here right in front of me. And this lab machine is now acting as a conduit to all of my Azure, application stuff. So I have spun up the application on a certain endpoint. Like if you were to just go back here, you can see that this is a public IP address that is given to my Azure VM. And on a particular port, I have this application running within it. So let me just show you the application, maybe a few relevant details about how this cloud thing itself is working. So I have a resource group that is created on Azure itself that uh, is hosting a container registry. And this container registry contains image files that are going to be pulled every time a new image is requested or a new container is asked to be spun up. This container registry is giving me all of that information. So what I'm showing you here is a Terraform script that contains several configuration files. Like for example, I have uh, how my identity is being set up, how my network groups are being set up, my network interfaces are set up, the providers that I have for this, which is just Azure in this case, how my public IP is being set up. Like I have a series of backend activities that have already been completed, sort of slightly abstracted away for for this use case. But the idea here is that an entire Azure environment has been created where an application has been spun up, and we happen to find out that application is now vulnerable to template injection attacks. So let us go ahead and try to uh, run an automated series of template injection attacks on top of that application. So let me just uh, run this application. All right. Let me just clear this a little bit. So I have template map already installed on this machine, and I'm just going to replace this IP address with the address of my application itself. Oh, sorry. Looks like I copied HTTP twice. Let me just correct that. And there you go. So now we see that template injection is in fact possible, and there are several plugins that template map is using on the backend, and it is testing against several possible versions of the parent language as well as the template engine that is being that could potentially be used. So it has identified several injection points for us, and it has told it. It now tells us that it is indeed a Linux machine that is being used in the backend, and the engine itself is called nunchucks, and you have possible shell command execution. You have reverse shells that is possible. You can write and read files. Basically, this application is very vulnerable, and the container it is running on is now potentially suspect to several other attacks as well. So let us take this example and push even further in. Let us break into the container itself and try to get a reversal on top of that. So we can try and read what is happening on the container within. So to do this, you could potentially just use a reverse command here, but we've noticed that if you do not have a netcat listener already on place, it doesn't work very well. So let me just do a slight modification to how the usual template map itself works. So what I will do is let me open up another terminal, and let me just start a netcat listener on port 1337, let's say. This, yeah. Now with my listener in place, let me run the reverse shell command here. And in this case, I will be replacing this public IP once more with my application's address. The same test is run once again, and you see that it does say that the port binding has failed, but that's simply because I already have a listener up and running. And in this case, you can see that I now have access to the underlying shell that is hosting this application. So to show you that that's the case, let me just run a simple ls command. And you can see I have the index.js file in here. Let me just show you what that is doing. Index.js. And you see the application code is actually available to us. We can see that it is built on, as the template map told us, that it is built on nunchucks, and it is available on a certain path, and the page rendering thing that we were exploiting, right, where it says /page, and it is concatenating the name of the query into this thing before rendering, which is obviously a very terrible thing to do. So now that we know we can actually we have access to the container that is running the application itself, let us try to do a little more of a permanent step here. So to break it down again, what we've actually what we've done so far is we've taken a vulnerable application, broken it, and showed you that template injection could potentially give you reversal access. There are other things that you can get, but if there is a possibility that there is some version of AppArmor or some sort of SC Linux commands running on the backend on your container, and you could potentially not be able to run OS level commands, like where we try to get into the we try to get a reversal itself. But there is a very real possibility that you could get file write or file read commands that could be passed in the form of the application itself asking those questions. But in this case, it was quite the effects were a lot more impactful, let us say. Now for the next step, what we have so far is simply one application, that is one instance of this application that has been compromised. But in a much more bigger sense of view, if we were able to rewrite the way this image itself has been written and ensure that the image is now has a permanent vulnerability that is inserted into the image. From this point forth, every time a new container is spun up, you are going to have a vulnerable container every single time. And that means any new application that has been spun up using this image is going to be vulnerable to a new listener. So it is possible that you have several listeners set up and ready in place, and every time a new application is spun up, uh, that new instance is also going to become vulnerable. And to do so, there is a pretty nifty little tool called Docker Scan. So Docker Scan is another open source Docker analysis tool, and this thing can be used to to look at the image files itself to see what sort of libraries are being used to perform some sort of black box and white box testing on top of your application. Uh, but it does have a pretty interesting little feature where you can modify the image and Trojanize it. So if you know that there is some input path available to you, you can use Docker Scan. In our case, we have a template map that has given us a reversal access, and the image itself can be accessed. I will show you quite shortly how that is possible. But once you have access to that, you can use Docker Scan to completely rewrite that image with a more vulnerable version of the same image that is going to have a reverse shell built into the image itself. So let us go ahead and build a new version of this image. And from this point forth, every single image on this container registry is going to be absolutely compromised. So going back here, let me just show you that you actually have access to Docker, uh, all the Docker containers and the images within it. So in this case, we have an image that is already a container that is running this particular application that we're looking at right now. Let me just see what images are available to us. And we see that there are two images. One is the vulnerable node application that has just been spun up, which we exploited uh, just now. And then there is another that says that's the Azure attack file as well. So let us try and modify this one. Now let us see what is available here. We have for the purpose of this demonstration, we already have Docker Scan installed on the VM machine, the Azure machine. But in the case of a regular exploit, you could then potentially, because you already have reversal access, you could then import Docker Scan from outside. You could install it from the internet and then continue the next steps. But in our case, we will simply use Docker Scan that we already have here and exploit a couple of variables and install Docker Scan on this machine. Now let's just go ahead and check if Docker Scan actually was installed. Yes, it was. Now I am going to install uh, Azure CLI on this VM. So from within the compromised VM, I am going to try and access the underlying Azure environment. And because I already know this is a Linux-based distro, I have a single line installer file that was made available from Microsoft themselves. Let me just quickly show you what that file looks like. Yeah, so this is simply a CLI tool to find out what version of Debian or Ubuntu you're using. And then depending on the architecture, it installs Azure CLI on your machine. So we did this because we want access to the underlying container registry, and we are going to get that very shortly. Okay. So with Azure CLI already installed, we are going to go ahead and get access to the underlying machine. Let me just quickly put that on silent. Yeah. Okay. So we now have Azure login that has given us access to the underlying infrastructure, and we're just going to make sure that the container registry, the resource group, is available to us on a single environment variable from this point forwards. So to show you what this does, let me just quickly copy this. So this lists the name of the container registry. It's a randomized variable for in our use in our case, and we're just listing every container registry that is available to us, and then ensuring that that is available to us later on down the line. So what we're going to do is we already have the Docker file, the image that is available to this VM. We're going to try and save that as a local file, and then we're going to modify that image and push it back into the registry itself. So while this will take a couple of minutes to like set up, so I'll just show you how that's supposed to work. So in our case, what we have done so far is we've taken an Azure VM, as in the vulnerable application has given us access to the Azure VM. The Azure VM itself has Docker installed on top of it. And we were able to use Docker scan that was installed inside the VM to gain access to the Docker image that we are going to be manipulating. And once we have access to the image, we will Trojanize the image to contain a reverse shell. And that reverse shell will be used to be pushed back into the container registry. And now every time a new VM is spun up, every single version of that image is going to have a reverse shell built into the application itself. So regardless of how many times it's spun up, it's always going to give us a lot more permissive action than anyone is supposed to have on a container. So hopefully this gets over in the meantime. Usually saving this image takes a couple of minutes. You gotta like, you're essentially saving a version of it and then rewriting the image file itself with a couple of extra uh, configuration settings that allow you to expose a certain port that you can then have access to later on. So while you're waiting for this, let me also show you what network security groups we have on this machine. So what we have done with this VM is, you will notice that the to showcase the vulnerability, we have actually set up a series of pitfalls. Let us say, like, this was designed to fail in certain ways, in the sense that the this particular VM actually does have SSH permissions enabled on top of it. So uh, if somebody were to get access to it, and from a public IP address, if they were to like ping the port number 22, they will actually get SSH access to this VM. Again, they should have the correct permissions, right? They should have the correct username and password string available to them. But regardless, the fact that it is allowed from any destination, so I mean any source address and to any destination address, is already quite permissive. And then we also have Docker that is running on two ports, port number 5000 and port number 5001. These sort of make sense because that is how the application itself is running, this front end application that we showed you. But the SSH is not a necessary requirement to run the application, and it is still present. Anyway, looks like we have the application already set up. So let's just go back and Trojanize this one. Oh, my bad. Let me just quickly get the server IP address. Oops. Okay. Looks like I ended the netcat listener by mistake on that one. Let's just quickly spin it up again. And there we have it. We have a netcat one more time. All right. Slight hitch there, but we're back. Now let's just cd into our Docker scan directory. And from within here, let's just make sure we have the new image loaded up. Yeah, we have the ASC Evolve Flask image already here. So now we're going to rewrite that image to have the Trojanized vulnerability. Let me just grab a new terminal. So what I'm trying to do here is I want to use this lab environment as my host. So every time a new reverse shell is being spun up on the new container, I want them to connect back to this one. So I'm using this as a host address that is going to be used to spin up the other containers so far. So let me just go back here. Give me 1 second while I just quickly pull up modified version of this. The command is hard to edit when your shell is not it's barely what it's supposed to be, right? Like this is a netcat listener. It's not even supposed to have this degree of access. Yeah, there you go. I was having a little trouble using my usual commands of up and down arrow and other things, but yeah, now we have it running as intended. This is going to take a second or two, but essentially what we're doing is we've taken the vulnerable, I mean, the Flask image, which is the application container image, and we're going to rewrite it to contain uh, a reverse shell vulnerability. The configuration settings are going to be changed, and from this point forward, every time a new image is pulled and the container is spun up, it is going to connect back to a port. The IP address 35.219.138, and it is going to be always on the port 4444. So from this point forwards, if I have a netcat listener available to me on my lab instance, which is where I found this. This lab instance is publicly available on this particular IP address, and if I were to start my netcat listener on 4444, I am going to be able to get reversal access to any new container spun up. Okay, looks like we've been able to Trojanize it. Let's just check what new image has been loaded. And there we have it. We have a new version of this image. It's just been written. Okay, so we have the Trojanized image, and we've managed to rewrite the old one and pushed it back onto the same container. I mean, we have loaded it back. Now we have a rewritten image file that we're going to try and push to our container registry. So, like as you see, it's got the same name as before, and it is going to be essentially replacing the the older, less vulnerable version of this image. So what I'm going to do now is log into my Azure environment, which I have successfully done. And I'm going to push this new version of this image. And now let's just make sure we have a netcat listener available to us on the port that we've mentioned before. And simply spin up a a new image with this particular, the latest version of this image, which we have done. And there you go. We now have access to the container without uh, having to go through the template map that we did before, where it was a template injection attack. Now we simply have the shell already built into it, and all you require is a netcat listener to be in place when the container is spun up. And you're probably going to be spinning up containers every time there's a fresh batch of load coming in, or if a new microservice needs to be pushed up, it needs to be scaled up. Regardless of what needs to happen, every time a new VM is spun up with this image, you have a ready vulnerability just open to be exploited. And so that about sort of wraps up what we were talking about in terms of container registries being potentially open to vulnerabilities. So in our case, we had an application that was vulnerable to template injection attacks, and we took that to the point where we were able to get reversal access to the container image itself. And then because that container image because the container itself was running in an environment that did not have sufficient network permissions, not enough IAM roles, not enough service account permissions, that were restricted to the point where the container itself was able to gain access to the underlying Azure environment. And with that, we were able to get access to the container registry itself, and we used that to to rewrite the image. And therefore, every time a new image was going to be spun up, it was going to be completely rewritten and contain the reverse shell ready to be exploited by an external entity. In our case, we had the lab environment's public IP and a port completely bound to that image. And every time the container would be spun up, every time a new VM was going to be spun up, it was going to be giving us a backdoor directly into the environment itself. So in terms of detection and defenses, there are, like I said, there are several layers of defenses that were missing here. And there is a primary focus on, for example, the application itself being vulnerable. So that was the input vector here, but you can quite readily imagine that the vector could come from several different points in the application, in the sense that the application could have SQL problems. I mean, it could be vulnerable to SQL injection or any other kind of code injection vulnerabilities. It could even be some sort of cross-site scripting attacks, or maybe some missing permissions that are then exploitable, in the sense that maybe some input validation is not happening, or perhaps there are some path reversal attacks possible in the way that the application template engine is rendering its contents. So with a wide variety of possible inputs, the defenses are going to come into play, where you shore up your application, then you shore up your environment, in a sense your uh, your cloud environment, and try to set forth boundaries, permission boundaries, for what is allowed by the application, by each VM, and what is available within your network security group, and how your container registry itself is being protected from being rewritten by unauthorized sources. And again, there are several ways the defenses can work in this, and we will talk about every one of them. Like the detection and defense stories are going to be quite involved, and that is what we'll be talking about in Black Hat Asia this April 16th. And please please stay tuned for that class.
Awesome. So thanks so much for that, Ganga. That was a great live session. So as you said, guys, this is just a tiny snippet of the full course, the attacking and defending AWS, Azure, and GCP applications. It's a mouthful, I know, but that's the full name of the course that is going to be available on Black Hat Asia between April 16th to 19th. And the seats are going away really fast, so you should really grab your seats right now if this is something that interests you. The link will be in the description below, so please get registered for that as soon as possible. You have less than 2 weeks left to get registered. So hopefully we will see you there, and until next time, bye bye. See ya.
Thank you.